Hey, Jordan.
Yeah. Hey. So how's your first semester?
Pretty good. Pretty weird.
Yeah.
But
Yeah. Well, were you a senior last year? Or no, I guess you were in college. Never mind. I was thinking my brain wasn't there.
no, it's okay.
Yeah. Where did you go to college?
Cornell.
Nice.
Yeah.
Nice. You should be in good shape then. Well taught.
Hopefully. Hopefully.
Yeah, it's kind of weird having an online semester, but I guess do what you can. Are
Mhm.
you teaching a lab as well?
Yeah. I'm teaching like 253A, I think.
Gotcha. Yeah. Yeah. Are they doing all they're in class, right? I guess
Yeah.
253 or 253B and A, I think, are both in class.
Yeah.
So I did 253B last semester and it was interesting, I guess, because I was thinking about how it would work because some of the labs, they'd have like 6 lab partners, because they didn't have enough equipment or whatever for that
Right.
specific, like Wheatstone Bridge lab. There was like 6 people in each group, where like 1 or 2 people did all the work and then 4 people just kind of watched.
Right.
So I wonder how they're handling that, not having no lab partners.
Yeah. I think for the mechanics lab, it's mostly just been like a lot of times you have to like click to record data and then like move something and like stop it before it falls off the table or something. So
Yeah.
that's been kind of
Yeah.
entertaining. But
Yeah. It's good to jump right in though and do 253 because there's nothing set up on the D2L itself, and I guess you get an intuitive sense of how to set it up yourself because you kind of have they kind of just like give you the reins basically and say set up
yeah.
your class and your pretty much everything.
Yeah.
So that was a little intimidating for my first semester as well. I was like, well, I've never even used D2L before.
Yeah, same. So was last semester your first semester?
Yeah. Mm-hmm.
Okay. Gotcha.
Yep. It was supposed to start in the fall, and actually I did start in the fall, and there was some weird stuff where with insurance or whatever they couldn't get. I had my own insurance and they couldn't get the insurance off, so I had to withdraw from my classes in the fall because I didn't have the money to just like outright pay for it.
Gotcha.
So I officially started, I guess, in the spring.
Gotcha.
Hello guys.
Hi.
Well,
The number of papers are increasing now. Earlier it used to be 1, now there are 2. When it reaches 6, I think then I can say we got normal. It's the same way it's supposed to.
I know from a teacher standpoint, I'm much happier for my students if they submit things either hard copy or a scanner, because the photos are hard to grade.
fact, before the semester, I just didn't accept a computer, even if they submit it, I'd say, take your time, bring back. So, very rarely that I accept it. Okay.
I accept it as proof that they did it.
Yeah, exactly.
They give me the hard copy if they leave you.
Yeah, exactly. Oh, yeah, everyone here? Yeah. Oh, everyone is nice. Does it zoom in more on this? I kept the same place that I usually do. Okay, good manage. Okay, so we wanted, oh, before that, homework and what? Oh, was there a homework today? Oh, it was postponed. Oh, okay.
Well, yeah.
So it was due today, right?
It is due today,
Okay. Oh, it is due, I guess.
midnight tonight.
Alright. So there's no class.
Do we have something on Monday?
Yeah. Yes.
Is it a holiday?
No, it's not a holiday, I think. Moses, you asked.
I asked last
So this
time.
is not a university holiday, it is for personal reasons.
It's a Dr. Shadish holiday.
Yeah. I think Moses was exactly that question. Don't get off from other classes. Okay, so, and we have midterm. Okay, so there'll be one more homework, right? So it's good to put one more homework. October 9, let's say. I have not posted it. I'll post it today. And your midterm 2. And again, this is,
I think it's a homework 4 that was due today. That you extended homework 5. You extended to the 7th, I believe. That's
I
right.
think that's math, but that's probably your thing.
Homework 5 is on D2L as the 9th, but that's because of something else, but it's on the,
As
on
the
the sheet
9th.
is today.
Okay.
Yeah, this is the one, Rob, you asked me, right? And I was all confused. So did I mess up this whole thing?
Yeah, I think homework 4 is said to be due tonight at 8 a.m. And then homework 5 is due on the 9th.
Okay, homework 5 is due 9th, you're saying, but homework 4, okay.
Yeah, homework 4 is due today. There was a mistake on homework 4, I think, and then
But this is due actually on October 2nd, right?
Originally, yes.
originally,
So we'll go by that, right?
Okay.
Then it was postponed for convenience, right? Or since others had other things going on. But as far as course goes, we can keep going and you guys keep submitting them. The submission dates are delayed, but so this is maybe 2/9, anytime. So that is homework 5, correct?
Yes.
So hopefully we can put in, let's say I'll put a small homework. Reasonable? Maybe I'll put one question there. Only one question, maybe. Depends on how the class goes too. Yeah, so we wanted to what is called macroscopic electrodynamics. Broadly, what we are talking about here is let's say, first of all, what are the sources? Let's say sources in electrodynamics. Typical sources. I mean, of course, there are many. We'll talk about that today in electrodynamics. One is, of course, a charge. Right. And yeah, how about this electrodynamics? So one is a charge, which means to say that an atom, typically, let's say 2 atoms, if they're interacting, an atom is typically by definition neutral, unless it's an ionized atom. So how will 2 atoms interact, let's say, electrostatically? And since they're neutral, one would think that an atom doesn't interact with the other atom, but is that completely correct? Right, so all of you guys are nodding your heads. So it doesn't seem like, so how would it interact? What can I ask that? So there is no charge. So in electrostatics, how would it interact? So there are 2 atoms, let's say. What is the interaction energy between the 2 atoms? Let's say 2 hydrogen atoms, simplest, right? So there is a positive charge and a negative charge going around it. Like this is how you model an hydrogen atom, maybe.
Talking about when they like share an electrons or
Share an electron. Let's say we keep it very far, really far.
There is some like dipole interaction.
Yeah, so this is neutral, but that doesn't mean that its dipole is 0. So its electric charge is 0, but this can act like a dipole. And what's the example of a dipole? Magnet is a dipole. So this is like having 2 magnets together. So they'll be significantly weaker than electrostatics or the standard charge interaction that we have, but it is there. So 2 atoms can interact that way. So second, we will say permanent dipoles. Right? And can you think of atoms that have no permanent dipoles?
Hydrogen ion.
But then
It's not an atom.
no permanent dipole and no charge. Let's say.
Noble gas?
Yeah, noble gas, exactly, right? Anything spherical, whenever it's a 1s shell, it is fully what do you call it? Fully filled, right? Fully filled, then it is spherically symmetric. S shells are spherically symmetric, and if it is spherically symmetric, it doesn't have any dipole, right? Good. So anything that has full S shells and no other shells, that's it. Or all shells filled, I think that's the best way to put it. Then it is, it's not just S shell filled, all shells filled, then it is spherically symmetric then it's a noble gas,
I
and then
I have one question.
Yes.
So isn't just L subshell spherically symmetrical? And the others
L-
are not?
no, L is not spherical. So L, if you recall, L, what do you mean by L? As P, right? You mean P.
I was gonna say D or F.
No,
Because-
there. So if you, I mean, we'll talk about it. So S shell, so that is S, P, D, right?
Yeah.
So S corresponds to spherical symmetric. P corresponds to these kind of shells, right? So there are three of them on X, Y, Z, if you want. Is that clear? And D gets much worse, right?
Two of these.
Yes, I think.
Cloverleaf.
So this is kind of something like that.
Yeah.
Yeah, right. Yeah, yeah, that helps. Well, that's five of them. Right? So they're not, as you see, they're not spherically symmetric. But S is spherically symmetric. But if you put all these three together, then they're spherically symmetric. If this is all filled, one together, they're spherically symmetric. In that sense, it is. And we'll try to talk about it. We'll start today very sketchily. We will do that today. It's called multipole expansion. But then more detailed, I think we're going to wait for a month or so for spherical harmonics to come in. But my question was, yeah, so charge. So if you have a neutral atom, then permanent dipoles come in. What if it has no dipole moment either? Like if you're talking about a helium atom, then what?
You can go to quadruple.
So then you can have a quadruple, right? And so this can keep going, right? And what's the next? Quadruple.
Hexapole.
Yeah, hexapole and so on, right? Good. So in general, they are called 2L poles. And L here could be 0, 1, 2, so on. It seems like L is just a number, but you have seen L as a notation in quantum mechanics also. That's exactly the same L. Right? That's exactly the same L that shows up, but interpretations are different. Okay. But we won't talk about quadrupole and all. Let's think of permanent dipoles alone. And what else can you have? So this is all statics. Now, what happens is that, let's say we have two helium atoms. They're perfectly neutral, no dipoles. And now you have two such helium atoms. Will they interact with each other electrostatically? I use the word electrostatically. Electrostatically, no. But now suppose I remove statics, then is it possible for it to interact? And why? How does that interact then?
And does Lorentz transformation have to do anything with it?
So what does statics has to do with it? So now, when we think of this,
If charge is moving, then there is magnetic field, and there's magnetic field, maybe somehow they react.
no, I would say no magnetic field. That's not needed. By statics, what the point is that this is spherically symmetric. There is a charge distribution which is perfectly symmetric. But that requires statics if you want it to stay there.
I see it now. So if we move kind of like
Just move the positive charge a little bit to the right, right? It's dynamic. For a moment, due to some disturbance, it gets disturbed. So it created a dipole for a moment. And the moment it creates this moves, this will also move. Like it's like two swings in a wind, right? There is a balance that you can have. So if this oscillates for some reason with some frequency, then it will make this also oscillate because it will try to align itself with that. So even if there are no permanent dipoles, some disturbance can actually cause induced dipoles, right? So then you can have induced dipoles. And So again, same thing. So you can talk about induced quadrupole moments, induced 2L pole moments, but we will stick to this. We won't be able to talk much about the induced dipoles. This is how scattering happens. We talk about that at the end of the next semester. Now we really need dynamics for that. So for example, how does scattering happen? So light comes in, that is an atmospheric particle that is neutral, and it induces some dipoles. So it is neutral, but it can induce a dipole in there. And the moment it induces it, then because the electric field is dynamical, it will start oscillating, and anything that oscillates will radiate, because oscillation has to do with acceleration, right? So that will radiate, and that's what we call Rayleigh's scattering. But that will have to wait. So we will talk about these two. So before we do anything, we need to understand what is this dipoles, quadrupoles, and so on. So what is a systematic way of doing this? This is called multipole expansion. So how many of you have done multipole expansion in some form before? Yeah, in some form, yeah. Have you roughly got an idea of that? So Moses, you have done? Anyone? Jordan, have you done multipole expansion?
I don't think so.
Yeah.
Yes.
Yes. Michael?
Very briefly.
Very briefly. Okay. Luke must have, right?
Yeah, we did.
Yeah. And you did it because I thought. Okay. So let's briefly do what is multipole expansion very quickly. So the idea is that let's, yeah, maybe before I do that, what's the dipole moment of a point charge? Single point charge.
Could it have a dipole moment? A single point charge?
Yeah. It seems like it is not reasonable to ask that question, right? Anyone wants to add on to that?
If we have electric field, then I guess.
If there is an electric field, why do you say that? If you have a point charge and you introduce an electric field, how does it change anything?
It doesn't.
It doesn't change anything.
If a point charge is at a point, how can you have any sort of dipole moment? I don't understand. Without introducing more charges or something.
Yeah, anyone else want to add? Actually, we will introduce that for a moment. For yeah.
Spin. would it?
Actually, good point you're saying. I didn't mean that, but probably, yeah, think about that. Yeah, I don't want to say no, but because I think the magnetic moment, moving magnetic moment can have a dipole, electric dipole moment. Yeah, I didn't mean that. Yeah, but I think you're thinking correct, probably, but let me not catch on to that. That's going farther than I want to go. Good thought, actually. Christian. Okay, so let me leave that open. Like point charge, does it have a dipole moment? Leave that open. We'll answer that. Answer is yes, I will, but I'm not answering. It doesn't make sense. Okay, but I can give a small hint to that. We have a force, right? Let's say there are force. There's a point. There's a mass, right? Some mass, and there is a force acting F in there, and torque is equal to R crossed with force, right? If it was a point mass, let's say, yeah, let me take the mass distribution out. If this was a point mass M, does it mean to talk about torque? What is a torque on a point mass on which there is a force F acting on it?
How could you have torque on a point? I don't understand that.
This is a mass M.
But you're saying it's just a point.
Yeah, it's a point mass. Can I have a torque acting? If there is a force acting on it, why not torque? R crossed with F. What is R then?
Depends on where you put the origin.
Ah, perfect, right? So it depends on where you put the origin, right? So it is a origin dependent quantity. Right? I need an R here, so let me change the direction of that. Right? So what is R? So if I were to place the mass on the origin, then the torque is 0. If I move it away, yes, there is a torque, correct? It will be very similar. In fact, it is pretty much the same idea that dipole moment is a very origin dependent quantity. And if you choose the origin in the right place, you can have a dipole moment. So for example, we always talk about, so how do we define dipole moment naively? What is a dipole moment? Yeah, define dipole moment for me.
It's the total charge times the distance between them.
Yes, the total charge, so first of all, you would say that is a negative charge, let's say, right, as show negative signs, that's a negative Q. Then there is a positive charge plus Q, right? And then there is a distance or a vector actually. So this is, let's say, A, right? And dipole moment, P, let's say, is Q times A.
Yeah.
Right? That's how we define dipole moment. It goes from negative to positive. But now let's say that I make this Q1 and Q2. Then what? Is it okay to have such a dipole moment?
We choose the origin.
Huh?
We choose the origin,
Choose the origin, yeah.
And
Does
there-
specify that better?
and you have two vectors, like one vector going to Q1 and another vector going to Q2.
Yeah.
And you take the triangular
Yeah, so
triangular
this is
addition.
R1, this is R2, correct? And I think what you're trying to say is P will be Q1 R1 plus Q2 R2. That's how you want to define this. Then why do we teach it like this? Why don't we teach it like this, however?
More convenient just to put the origin of one of the charges.
It's slightly more than that. Now, what happens is that if the charges don't balance to 0, then dipole moment doesn't have much meaning. It is an origin dependent quantity. If it is not 0, it is an origin dependent quantity. And if it is origin dependent, then if I ask you guys to calculate the dipole moment in an exam, all of you will have different answers because all of you will choose your own origins. So dipole moment has no, if you were to measure it, how does the experiment know whose origin am I supposed to do? So dipole moment doesn't have much meaning unless the charge is 0. If the charge is 0, it becomes origin independent. And that's why you always define it like this. This is reasonable. It can be more than one charge, it doesn't have to be one charge and so on. And the same thing goes with the next moment. Like in gravity, for example, why don't we talk about dipole moment in gravity?
Because the masses are not same, I guess. The masses are not same. Same here. The charges are
And try
not
that
same.
again. Try that better.
So,
It's because it's not an origin dependent quantity, right? It is an origin dependent quantity, so.
Yeah, and why is it origin dependent?
Because as he said, the masses are not, unless they sum to 0.
When will it sum to 0?
there is antimatter.
Yeah.
No, not antimatter. Antimatter doesn't have negative mass.
Something that has negative mass.
What has negative mass? Negative mass doesn't exist as to our knowledge, right? Negative mass doesn't exist, so you don't talk about that for moment in
You
gravity.
were talking negative mass,
Yeah.
then you should answer right.
Now he will answer more than what is needed, probably. That was a popular topic. But, okay, maybe extra credit, this is just for general knowledge, so extra credit. Going very far from where I wanted to go to. Gravitational waves require a certain moment, right? Certain kind of moment in a distribution. What kind of moment does it need? Or does a dipole, does a mass with a dipole moment radiate? What do you need in a mass distribution so that you can have gravitational waves? All of us know what is a gravitational wave at a popular level. I don't expect it to be very detailed level. No, I probably not. Gravitational waves? Yes, no, right? Okay, so the question is, what kind of mass distribution? What mass distribution in the sense of dipole moments, right? What distribution causes gravitational waves? Okay, that's just for a general knowledge. Okay, so all this seems to talk about multipoles. So very quickly, let's define what a multipole is. It all stems from 1 over r minus r prime. And what is this popular part? What is this? When you see this expression, what does it look like physically? 1 over r minus r prime. In gravity or electrostatics, as a potential, right? 1 over r, right? That's an energy associated with a point charge. Let's say r prime is its position, r is the observation point, right? So if you really want to give physics to this, it's q over 1 over 4 pi epsilon naught, correct? So that's the electric potential due to a charge at position r prime. So this is observation, this is source of the charge. This is observation point, observer point. But let's do it as a mathematical exercise. Forget the 4 pi epsilon, forget the q. We'll bring it back after we have done this. Taylor expand this. Just Taylor expand this about r. How will you write that? If I were to ask you guys to Taylor expand that about r, so what will be the first term? If I ask you guys to Taylor expand this expression about r, so what will be the first term in that case? Just r, 1 over r, right? Magnitude of r, so that's 1 over r, right? Okay. Second term. Taylor expansion.
Wait, sorry, are we expanding over r or r prime?
Over r.
Okay.
Right? F of 0, right? Isn't that? Okay. Let's do this. So f of x, right? Let's do this instead. F of x is f of 0 plus, how do you write this? Help me here.
F prime.
Then you will do x times right, x times d by dx
of f of x at x equal to 0, all right?
Yep.
And that's all right. Okay, so now let's say I want to do f of x plus x prime. That is x minus x prime actually there. So how will I expand this? I want to expand about x, so I'll do f of x. Correct? Isn't that? So this is expansion about 0, right? Isn't that correct? Am I taking this right? Okay. So this is plus x prime times d by dx of f of x at x itself. So it doesn't matter. I don't have to specify that, right? At x equal to x. So that's that x prime. Is this correct? Yeah. Am I right? Help me here. Is that how you write it?
I just vaguely remember this Taylor expansion, like when we were expanding f of x minus a, then we would have x minus a. Kind of
So how, okay, tell me your Taylor expansion. Okay, tell me. What is the Taylor expansion you guys know?
It is not just be 1 over
F of x minus a, okay?
and f of a. If we
Oh,
expand
you
about
wanted a, I see. Oh, a plus x then? Is that how you want it? Or you want to write it as x minus a?
No, I thought x minus a.
X minus a, okay. Is equal to, yeah, tell me, f of,
if we expand this about a, then it will be.
oh, about a,
Mhm.
okay? So
F
f
of a.
of a, the minus a then, right?
No, f of
It
a.
will be just f of a.
F of a, really? Okay.
Plus f prime of a, so which is just differentiation.
F prime, so okay, d by dx, oh, yeah, f prime, right, d by dx of x equal to a, right? And what is this now?
X minus a.
Mhm.
X minus a,
And I think so.
here.
And
Then this is 0, right? Oh, this is, oh, no, x minus a, this is okay.
that x minus a is not evaluating. It's not evaluated. It's a different thing.
Yeah, I think this is okay. This is okay. Okay. So
And
this
then
is,
that will
yeah,
be
yeah,
x
okay.
minus a whole square over 2.
Yeah, nice. Okay. I think it's just that I would have seen this as a plus x. Okay, let's see. If I can do this. Okay.
So in that case, we're expanding about a.
Mhm.
Yeah, we are expanding about a, right? So
Yeah.
isn't this a plus x minus a? No, we are x.
No,
Minus a.
So I think if we expand, if we have f of x plus a, then it would be f of minus a.
Okay. Give me a second. Let me. I want to get. So this is your formula, right? I don't remember. I don't see it this way. So you want me to motivate this? Okay. F of a, right? X equal to a.
I mean, we can try.
Yeah. If I put x equal to a, this is 0. Yeah, that's the point.
We can.
Right. Yeah. So if x is equal to a, right? If x is equal to a, this becomes f of 0. How do I get that? If x is equal to a, okay, this cannot be correct. I don't understand. Okay, x is equal to a. If I put x equal to a, right? This is f of 0 on the left, and this is f of a on the right. How can this be correct?
I think your third equation, like our formula, simplifies to the top formula as a goes to 0.
Yeah, but I'm saying in this equation, correct? if I put x equal to a, right, I put x equal to a,
Mhm.
I get f of 0 on the left. Here, every term is 0. And this is f of a. So I'm saying this cannot be correct. So why do you guys say this is, look it up and tell me.
I don't know. I just do it from the definition.
Yeah, so give me a definition. I mean, I'm saying this has some problem unless I'm missing something. Help me here. So you guys gave me this definition, and most probably it is correct because all of you guys, there seems to be 2-3 people saying it. So what am I missing here when I interpret it like this?
I don't use that
Maybe
definition.
what Luke said makes sense. There must be an implicit assumption that A is going to 0.
No, I mean, this is wrong, right? Or at least it seems to me to be wrong. So I'm saying there is some, but you guys are saying that you guys use it. I don't know. Wrong.
Jordan, what's the definition that you use?
I just go by the full definition or whatever. Just
So what is the full definition? Give me one definition.
f of x.
I think that is correct.
This is correct.
Mhm.
This is correct. Okay. So how does you say when x is equal to 0? So let's say x equal to 0 doesn't help. X equal to a. Right? How do you help me with x equal to a?
Oh wait.
This cannot be correct. I don't think this is correct. Help me here.
Right. I
So now
think
there's two people saying-
so. So the right hand side is correct, but I think
So
the
left-
full definition is f of x equals the right hand side about x equals a.
Better. Okay. F of x.
Yeah.
Okay. Okay. I like that. Okay, good. So this is a correct definition, right? So let's write this as, okay. Now I want to go from here to there, right? So somehow get this. So let's say f of x, I would like to do a. I want to keep this as it is. This
I think you
is,
should just write the full definition. Like I feel
Yeah.
like writing the full definition is more helpful than trying to piece together.
since I started with this, shall I go with this?
Yeah, that's fine.
Maybe, okay. Okay, well, let's just do this. Okay, x minus a and a, right? Right, I just added and subtracted a here. Right, so that's f of a and so on. Same thing. I don't do anything here, right? Keep everything the same. That's perfectly fine. Let me define x minus a as y, let's say, or x prime, right? X prime. X minus a is x prime, and a is, let's say, y, which I want to replace it with x. So this is f of y plus x prime. That's equal to a is y, so this is f of y plus x minus a is x prime, df by dx at x equal to a, which is x minus x equal to a. What is x? So x equal to a reads a plus x prime is equal to y, and so basically y, right? So this is f, so this is y basically, plus x prime square over 2 factorial times. Better?
So you said a plus x prime is equal to y.
A is equal to,
Because you have
I said, this one I'm saying is x prime because I want to compare with that. And this one I would like to call it x, but I don't want to confuse with this x. So I'm temporarily calling it y. That was my motivation. Okay. So another way of writing the Taylor expansion if you want. But for useful for this purpose. Then we don't, I think the only goal here is that then I don't have to set this x. Okay. Is this okay? Are we good? Is there any concern on this? Okay, yeah, so if that is the case, so this is x plus x prime, so I can do that, right? So now notice, this is x prime times d by dy. If I were to extend this to vectors now, so this is x vector plus x prime. We just had to upgrade ourselves to gradients then, right? And vectors. Then this is f of x plus. And then x prime now, this is a vector x prime. Dotted with d by dy is d by dx, that's a gradient. Right. Acting on f of x, actually. So the gradient acts on f of x. The next one will be double of this. And it is okay to write the double because gradient never acts on the prime. So it will always come out. So this is, you can write it as a square. It's convenient to write it like this in this case. Times f and so on. In fact, it's not necessary for our purpose. You can actually think of this as 1 plus x prime dotted with gradient plus x prime dotted with gradient square over 2 factorial and so on, acting on f of x. Notice again, one might be worried that, oh, does this commute, what does this x prime go through? X prime does go through because the gradient doesn't act on that. What is that series in the brackets, familiar series? Should be a familiar series.
That's like exponential.
Should say it's exponential, right?
Exponential.
Good, right? So exponential, if you think of an operator on the exponential, so this is x prime dotted with gradient of f. So in that sense, so if next time if I were to tell you what is this f of x, that's equal to
F of x plus x prime.
f of x plus x prime. So this is usually thought of as a translation operator. Right? So the derivative here is a translation operator on this function. So there is a similar thing called rotational operator. So group theory begins from here, but we won't get in there. So this is the idea of group theory where you think of this as an operator. And this is the parameter associated with that operator. So translation operator is d by dx. This is by how much you're translating. That's the way to look at it. But we are not going to do that. Here, we just want these terms, right? So this is plus. Here there is minus, right? So this is minus r prime. I have a minus sign there. So minus r prime dotted with gradient of 1 over r. Next one is double of that. So plus and the minus sign goes away. So that's 1 over 2 factorial. And then there is r prime dotted with gradient, and then there is another R prime. Again, but put the brackets prime dot with gradient. Remember, any derivative operator acts on everything on the right hand side unless the bracket closes it. And this is 1 over R plus okay, that's it. Okay. That's it. Okay, so that's all I need. This, if you want this multipole expansion, but we haven't done the interpretation yet.
Is R still a vector?
Yes, this is a vector
R
dot.
prime, but R.
No, this is a magnitude, right?
Okay.
F of
Oh,
you
I
have
see,
set
I
to
see.
0, then that magnitude of that
I see.
is R, right? So remember, this is the electric potential due to a point charge at the origin. Remember your torque, right? Things
Yeah.
get simpler when
Yeah.
you're at the origin. That's the basic idea here.
Yeah, right, yeah.
You want everything to go about the origin as much as you can. Like in statics, I think it is statics in engineering. When you're doing statics, you write the force equation and then you write the torque equation. Right? Is that familiar idea? Right? You first write a force equation, then you write a torque equation. Are these two independent all the time? It's only when the force equation is 0, forces are balanced out. If it is statics, then the torque equation has a new meaning, has an independent meaning. Otherwise, it's typically information content is there. And so that's broadly what the idea is here. Or there's a connection between those moments, right? So the dipole moment, like that also is a moment of a force, right? So same idea. Okay, so let's see. We want to process this now. We know how to operate this, right? This is 1 over R. What is that equal to? Quickly, immediately, after all the vector calculus.
R over R cubed.
Yes, good. So minus R hat over R square. Let me allow me to write it as R over R cubed, right? The negative sign, that negative sign goes away. Nice. That's so basically take the derivative with this, and then the idea is the gradient of the magnitude of R is R hat. That's all. That's one thing, one identity you should remember. There's one more identity I ask you guys to remember, and that is a coordinate independent quantity. This is static one. If there are two vectors coming, the gradient of the position vector is the dyadic one. That's a completeness statement. Then we don't have to really operate this all the time. So this one was quick. Same thing here now. Notice R prime can move. Let me write one more step here.
So you wrote minus R over R cubed. Is that?
Yes, this is a minus, right? Because 1 over R differentiation gives you 1 over R squared.
Yeah.
Minus 1 over R squared.
I'm just thinking in terms of the problem. Isn't
Here, you
how
mean
it give you-
that will kill the negative sign there.
Mhm.
Or maybe you're thinking ahead of me. You're concerned about it?
Yeah, but just go ahead. Yeah, just go ahead.
No, it's okay. I think that's should be there. That will kill that negative sign there. That's necessary. Let me actually put this in there right away. So this is R prime dotted with R over R cubed, right, plus, let me rewrite this in a certain form. This is 1 over 2 factorial R prime dotted with this term allows you to do this. Now notice the second R prime, I can move this R prime wherever I want to as far as I dot it with this, because this gradient doesn't act on this. This gradient also doesn't act on that. So I can move it left or right. So I write this as gradient 1 over r, but this bracket signify that this gradients don't act beyond that, and dotted with r prime. Actually, I don't need that parenthesis actually. Is that clear? This dot means that it acts on the right vector, this dot acts on the left vector, and this is a dyadic now inside. Just like rearrangement there. And then I know how to operate this. That's a dyadic quantity. Let me operate that. So this is gradient 1 over r. So goal is going to be, this is going to be monopole, this is going to be dipole, and this is going to be quadrupole. Quadrupole is going to be dyadic now. But let's see this properly, how this is defined. This is gradient negative of r over r cube. This I know how to evaluate. This is negative. I can act on the numerator over r cube, or I can act on the denominator. And the position of the indices has to be kept on the left or to the right. This is 1. It's minus 1 over r cube. And this is now do the same idea. When I differentiate this, this becomes r raised to 4. So this becomes a plus, first of all, r raised to 4. And then there is an r hat. But r hat, I want to write it as again r over r. Right? So, and that is a 3. So this is 3 vector r over r raised to 5. And that is another vector. So that's the same as writing it 3 vector r minus, I want to make this r raised to 5, so I multiply this by r squared, and then there is 1 divided by r raised to 5. Little more processing here. Now, rest of it is just rearrangement. So let me write this. Oh, I move the camera before I do that. Can I move the camera? Are you guys copying stuff?
Yeah,
I'm good.
Good.
I'm good.
Okay. So, oh, this had a problem, right?
I guess my question was, whenever you put the plus into Coulomb's like general formula, and then you were to solve that, you'd end up with a plus sign instead of a minus for your dipole. That's what I don't understand.
Tell that again. Sorry. Tell that again. I think I can understand your question.
So yeah, when you put the plus sign, when you put the 1 over r plus r prime dot r over r cubed into the formula for Coulomb's general, like just the general form of Coulomb's law, then you're going to end up with a plus term instead of a minus term. You're going to have your dipole formula is going to be 1 over 4 pi or q over 4 pi epsilon naught of this plus the next term. That's what I don't understand.
Let's wait. Okay, I think you're going ahead. Yeah, so I'll come to that. Okay, put the thought. I think whenever I define that, it should be okay. Yeah, I think you're ahead of me of that. Okay, so I'll be doing whatever you're saying, but maybe there is a difference in the way you are seeing and way I'm going to introduce it. Maybe. Okay. Let's give me a few minutes. I'm not saying you're wrong. Let me proceed and then I'll come back to it. Is it now?
Yeah. Mhm.
Okay. So again, writing, repeating this. So this is R minus R prime is equal to 1 over R plus R prime. Maybe remember this is source, right? That's, oh, yeah, the leaf.
Yeah.
R prime dotted with R over R cube plus, right? And let me put that in. So this is 1 by 2 factorial times R prime dotted with, this is 3 vector R minus 1 dotted with R prime. This whole thing divided by R raised to 5. And the next one is not easy to write using vectors. Yeah, Nasa?
Where did that R square go?
Where did that R square go? Because I missed it. Can
Can
you
you,
tell us? Is that correct?
I was just gonna say, can you just say 3R hat over R cube?
Yes, but I want to identify something.
Okay.
So, in general, yes, but that's going to become the quadruple moment. Notice that this is symmetric in R and R prime. I can swap this R and R prime, this and R and R prime. I can swap that, and that's perfectly okay. What I mean to say is that R prime dotted with 3 R minus 1 square dotted with R prime is the same as vector R dotted with 3 vector R prime sources, right? I want to interpret this as a property of the source, like the quadruple moment. I want to write it like that. Okay, that's the same. So I'll get lazy here. You guys cannot erase unless you're using pencil. This is prime square. Nice. Okay. Good. Now I introduce my 4 pi epsilon naughts, right? Copy this again. So this is Q over R, a single chart. This is equal to Q over 1 over 4 pi epsilon. Leave some room. Leave a little room. I'm going to put a summation sign also if you want that. Q over R plus Q R prime. Notice this. I'm putting this together, put it in a bracket. Dot R over R cube. That's a property of the charge. How far is it from the origin? So the momentum of the charge, if you want. Plus, leave some room here, leave some room here also if you're writing. This is 1 over 2 factorial, and this is R dotted with Q times. Leave room here again. So Q times 3 R prime minus 1 R prime square dotted with vector R divided by R cube. Okay. You concerned, Avinash?
Kinda.
Or
So
did I mess up?
why did we not build 1 over 4 pi epsilon naught in second and third term?
Because that's a unit. Because I'm not an SI unit.
Well, if you put that in first term, you also have to put it there, right?
Yes. So minus.
You just put it outside of the bracket.
Oh, yeah, that's also good.
Yeah.
Then I have room there. better. So this is for a 1 point chart. Typically we have more than 1 point chart. How do I introduce that? So if there are many point charges, superposition works. So I'm going to make it 1, 2, 3, right? So this is Qi or I and sum over I. Right. So I introduced an I here, position or I. We'll do that for everything. So this is observation point, no I is there. So that's summation over I. So that's one. There. I, all the observation points, sorry, source points have an I. And that is an I. And all the source points have an I square and sum over I. Let me define now a monopole of a charge distribution of sum of charges to be sum over all the charges. If it is not point charges, if I have a charge distribution, this will be integral. Instead of a sum, this is an integral. And instead of Q, I will have a charge density. That's the monopole. Total charge due to a charge distribution. Dipole, definition of a dipole now is this quantity. If there are point dipoles, it is Qi times Ri vector prime, right? Is a source dependent quantity. If I am doing a charge distribution, continuous charge distribution, the generalization is d cube R prime, and this is vector R prime and rho of R prime. Like that's a first moment. In Newtonian mechanics, what does this remind you of? What's the connection between this and Newtonian mechanics?
Moment of inertia?
Moment of inertia is two
Or
of them.
something like that.
Square. Yeah, something like that. What is that?
Um, Center of gravity, maybe?
Yeah, center of mass.
Center of mass.
Right. It is center of mass times the total mass. The center of mass is the position times. Yeah, very good. Right. This is an analogy with center of mass. Good. Quadrupole moment will be a dyadic. Right. Quadrupole moment is a dyadic. Sum over I, Qi times 3 Ri primes minus 1 I prime, sorry, Ri, right? Yes. And that's equal to integral I don't use the vector. The integral, volume integral. And this is 3 vector prime so this will have the idea of moment of inertia. Right? Moment of inertia tensor, I think is familiar. Are you familiar with moment of inertia tensor?
Yeah.
I'm familiar with moment of inertia, but not potential one.
Yeah. So, for example, what's the moment of inertia? Moment of inertia is axis dependent, right? So, axis, where you choose your axis matter. So in general, you can choose anywhere, any 3 axes. And that's tensor. Okay, so that's your dipole, quadrupole moment also for you guys. I think that's slightly cutting off on the video, but I think it is, you can fill that in, I suppose. So this whole thing is equal to 1 over 4 pi epsilon naught, 1 q over capital Q over R, capital Q over R plus P dotted with R over R cube plus 1 by 2 factorial of R dotted with Q quadrupole moment over R raised to 5 plus, what's the next one? What's the next one? You cannot write it like a vector. So what do? You cannot, it's hopeless to think of it, to write it as a vector. So what do? What else? I mentioned something.
You put dot, dot, dot.
Very good. Very good. That helps. Writing that is what is called spherical harmonics. Right? This series is done if you're doing on the axis. This is Legendre polynomials. If you do it in general, this is spherical harmonics. Same angular momentum L, same m's. So this will be L. So this is L equal to 0, monopole. L equal to 1, dipole. L equal to 2, quadrupole. Same, there's a reason why it is L, same as the hydrogen atom. It is the angular momentum, it is the spherical harmonics. So Legendre polynomials.
Is that still extra credit?
So I answered it. No, don't try to write it in terms of vectors. I think it's not guided. Yeah, do something. Yeah, read the connection between Legendre polynomials and multipole expansion. How about that? And I typically at this stage, whenever I introduce Legendre in the course, I tell if you want an A grade in the class. Did I say that before?
Yeah, I think you did.
Yeah.
I'll
So
find a picture of Legendre.
yeah, get a picture of Legendre from the internet. Okay. If you get the picture of Legendre from the internet, then you get an A grade immediately.
We did, but we did not.
So that's a joke. No, don't take me so by chance if you get it. So the point is they are missing the portrait of Legendre. So it's a nice story. Look it up. So it's a very nice story. Have I told you guys?
Yeah.
So
I think I know this. I think I can tell this.
Yeah.
So they're like, all the time, like they were thinking of some other French guy as Legendre because they had the same name.
Okay.
So they were missing Legendre for somebody else.
Okay. Interesting.
Yeah, so I think the point is that so there Legendre is a normal common name in France apparently, and there's another famous man who was a military general. So for 200 years almost, like this was in 1810 and so on. So almost at least 100 years or more than that, 150 years, they have been circulating a portrait of Legendre. And everyone thought that's what it is. Every book has that in its name. But in the last 10 years, with the digital digital technology going up, again in France, some graduate students found that there were two images, two persons were associated with the same portrait. One was a military general, and the other was this mathematician. who is more popular actually. But then it was realized that the portrait they had was not of the mathematician, the genre. So then the question comes, where is the picture of actual the Legendre, right? And they still don't have it. So that's a for historians, that's a big challenge. We want to figure it out. So it's kind of a little embarrassing for the academic community
Maybe,
that they were using a wrong picture for almost 200 years. So, a small circumstantial story. Yeah, that's all. So from this point on, I will take this up, and we want to. So the main idea was that dipole moment. Right? We want to do this dipole moment and now define it for a charge distribution, but basically a collection of atoms. We want to talk about what is the dipole moment of a collection of atoms, and that will become the property of the material. So a continuous material, when we think of a plastic or a wood, what's the electrical property that interacts with something else? So it is going to be the dipole moment that will interact with it. And we want to define it for a macroscopic object, for a table, for example. We want to define the dipole moment for a table, which is neutral, but still has some electrical property. And that will be called polarization. So that's the purpose of this. Okay, thank you. 2 minutes first. Oh, Jordan, did I clarify? I think you had a question. Yeah, those who want to leave can leave.
I'm muted. Sorry. I was saying, no, you didn't clarify my question, I guess, but
So still we have, so you think that negative sign is still not satisfactory?
yeah, I don't understand. I feel like it should be negative, or you'll end up with a positive for your dipole, like your potential.
Maybe the point is
with Q over 4 pi epsilon naught r plus 1 over 4 pi epsilon naught r cubed.
Does this help potential, electric potential? We have not done this here. Electric potential due to a point dipole is P dotted with R over R cubed. So this you can independently, suppose you have a point dipole, so two charges comes together so as one point, so then that's what this will be. So since you have not done that, I couldn't motivate in that sense. So it seems consistent to me, but I'm not sure whether I see what you're looking, the way you're looking.
I don't know. I guess I don't know how to explain it, but you're taking it a approximation for at least for this part, you're taking an approximation for the general formula of the potential.
It's an approximation in the sense this is the first term in the series. Yes, that's correct. If I drop this, then it's an approximation. If I don't drop it, it's exact, right? Yeah, think about it. Maybe come back to me because we will talk about this again.
Yeah. Okay.
Reasonable? Yeah.
Yeah. I'm just thinking about if you plug it into if you plug the expansion into the general formula.
What is the general formula?
Sure.
Just the integral of the charge distribution at r prime multiplied by,
I think you're having this in mind. Is this your point?
hmm
Right?
yeah,
And here you would like to introduce what? Now rho prime for a dipole is different, correct? It's not the normal way.
yeah. So now you have rho prime times that Taylor expansion, which is a positive.
Yeah. Okay. Yeah. That's okay. That's fine. Yeah. So that Taylor expansion. Yeah, that's perfectly fine. So let me, if you allow me to write only the term there, that's this, correct?
You're just leaving off the 1 over R.
No, this was one of, oh yeah, I'm just taking the second term. Yeah, exactly. Only the second term.
Okay.
It look like this, correct?
Yeah, I was thinking about 1 over R minus R prime, but yeah, go ahead.
Yeah, so if you want to write that also, so this will be d cubed R prime, rho of R prime over R if you want, right?
Mm-hmm.
Yeah.
Yeah.
So then this is the dipole, because this is only R prime, this is an integral, right? This all can be done. So that will be the dipole, which is consistent with, yeah, that's correct. Yeah, so you're saying correct. Yeah. So no sign, right?
Well, coming through that, you got a positive instead of a negative. That's the difference.
Yeah, but this is the positive. Yes, this is P, but this is positive.
Mm-hmm. Yeah, but I'm saying it should be negative because if it's positive, then whenever you look at the what word am I supposed to use here? When you look at the dipole moment formula for the potential itself, you should have Q over 4 pi epsilon naught R minus 1 over 4 pi epsilon R cubed P.
Maybe, okay, slow down. Okay, so Q over 4 pi epsilon naught
Yeah.
times?
Epsilon naught R or 1 over R, however you want to do it. Minus 1 over 4 pi epsilon naught R cubed.
But this is not yet there, right? You don't mean that.
P R cubed P dotted with R.
How? Okay.
Then you multiply your dipole moment on the right side times.
No, dipole moment comes from this expansion, right? What you would say is that there is a charge Q at R plus R1, right? R minus R1, that's the position of the first charge. Right? Let's say it's on the Z axis. And then you will put there is a negative charge, 4 pi epsilon naught. And then there is R plus R1, right? And then you expand this out.
You expanded the one. You expand the 1 over R minus R1, and you get what we did basically.
And you'll get a plus, right? This will be plus. 1 over x minus y is plus, right?
Okay, that's where my mistake is then, I guess.
Yeah, I think it will work out because it's exactly the same thing. Yeah, exactly. Yeah. Yeah, check it out. I think it seems consistent to me, but yeah, look into it.
Okay.
Yeah.
All right.
Seems okay. Yeah.
I think that answers my question, what you just did.
Yeah.
Okay, thank you.
Okay, good. Yeah. Okay.
Bye.
Okay, enjoy. Helps.
Yes.
Mm-hmm.